So here is another example, okay, where I have a carbonyl group and sulfur, and I have OMe group, I mean COMe group. Okay, so how to synthesize this particular molecule? This is a target molecule which I want to synthesize. So based on our normal polarity, okay, so what is the normal polarity? If I want to have anything, I want to add at this alpha carbon. Okay, what is the alpha carbon? This is my alpha carbon. This is another alpha carbon. Since the molecule is a symmetrical molecule, whether I substitute this particular position or this particular position, it's one and the same. Okay, so you know the carbonyl oxygen is going to be negative charge, and this is going to be a positive charge. So this is going to be negative charge here. Which one? Alpha carbon is a negative charge. Okay, beta is a positive charge. Like this, I can keep on extending it. Now, I want to synthesize this kind of molecule where in which I have an what you can call as a heteroatom. What is the heteroatom present here? So sulfur is your heteroatom. So I'm going to have a negative charge here and positive charge, a negative charge and positive charge. Okay, so this I can call alpha sulfonylation as okay. Okay, I'm going to introduce some group at the alpha position. So when I want to introduce some group at the alpha position, what should be the nature of that? It should be a positive charged one. It should be an electrophile. I hope I'm clear. Okay, because it's a nucleophilic carbon, so I can add an electrophile. That's what I discussed in the last class. I can add an alpha halogenation here. Now the problem is that I'm having a heteroatom at this particular one. So if I'm going to have a carbon based one, no problem. I can have a simple system like a R plus, I mean CH3 plus, I can add at the alpha position. So it's very simple alpha halogenation kind of one. Now I mean alpha alkylation. Now instead of carbon, I'm having a sulfur atom. What is the nature of sulfur? Sulfur is a more electronegative. Sulfur is a more electronegative atom. So you cannot have electronegative. So you cannot have a simple system where you cannot get that particular negative charged species. So as a result, I must have what you can call the charge. Okay. So what should be the charge on this? The charge on this particular one should be some sort of a what you can call a positive charge has to be created and then negative. So now I can have two types of retrosynthesis. One where I'm going to have a CS disconnection. So CS disconnection. Okay, here also is a CS disconnection. CS disconnection. Okay, so when I'm going to have a CS disconnection, I can have two ways. One where I'm going to have a negative charge and sulfur is going to be a positive charge, where I have a CS2 COOMe. Okay, fine. So what is the other one? Other one where I'm going to have a positive charge at this alpha carbon, okay, and then a negative charge at the sulfur atom. Okay, so now as per your what you can call the polarity aspects, what should be this the alpha carbon? So alpha carbon should be negative charge. Yes, this particular way I have a negative charge. There is no problem at all. Okay, but I need to have the suitable substrate with this particular positive charge. So this is not possible at all. Okay, as a result, sulfur cannot have a positive charge. So as a result, I cannot go for this kind of CS disconnection. So what I must do, I must have the what you can call the polarity which is the inverted one. Okay, so I can call this is a inverted polarity. Okay, it's also called as opposite polarity. Okay, so what is the opposite polarity? Means a carbonyl alpha carbon supposed to be having a nucleophile, but I'm creating a positive charge here. Okay, how to create a positive charge? That can be what is this corresponding? The substrate for this. The substrate is a very simple. You just take a cyclohexanone, cyclohexanone, and add a negative charge species. So for example, bromide, Br minus. So if I have a bromide at this alpha position, I can do, okay, I can create a positive charge. So now this particular starting material synthon can give rise to this kind of this kind of the intermediate positive charged ones here. Okay, so by eliminating a Br, I can able to get a positive charge on this. So this kind of reagents are called homolong. Reagents. Okay, means reagent which going to give rise to opposite kind of a charge on this. Okay, so what is the corresponding the starting material for this? It's a very simple. You add a H plus to this, S minus. So I will be getting a CS2 COO Me. Very simple ones here. Okay, the thiol SH CS2 COO Me. Okay, fine. So now whenever you have this kind of what it calls the polarity, it is going to be inverse of this normal polarity. In those kind of cases, you must use this kind of what it calls reagent, which is going to give rise to opposite polarity species. So those reagents are called homolong reagents. Okay, so this I'll be discussing more number of example. I'll give you more number of example related to this kind of what it calls homolong reagents, where I have a opposite kind of polarity. Okay, so now what is the synthesis part? A synthesis part is a very simple one. You take a cyclohexanone. Okay, now if you want, you can also further analysis, do the analysis. Okay, how to synthesize this kind of alpha halobromine? You take a cyclohexanone, okay, you do the alpha halogenation, means you generate an anion here. So this anion is going to have a inlet ion. This inlet ion is going to form a double bond, C double bond O, and this is going to attack and Br is cancelled. So you will be getting an alpha halogenated. Okay, so cyclohexanone is a very simple starting material. You do the alpha halogenation to get this compound. Okay, use this alpha bromo cyclohexanone and with your thiol. Okay, so thiol having a 3 carbon, so 2 carbon, CS2 COMe ester, and then you can do this. Okay, so you take this alpha halo ester, so alpha halo ketone. Okay, you synthesize, you just treat this with a base. Okay, so you will be getting a alpha halogenated and generate an anion. So again, you just take add a base to this. Okay, so the base is going to form a negative charge here, deprotonation take place, and Br gets eliminated. So very simple SO2 kind of reactions, where I'll be getting a CS2 COO Me. Okay, so now you can see you are going to do opposite to that of your normal polarity. So this is called inverted polarity. Also these reagents are called homolong reagents. Okay, fine. So now let me okay, okay. Now I just want to give you one more example. Okay, so here is a case. I want to have a difunctional group. For example, you take a 1,2-diketone. Okay. So what is 1,2-diketone? I have a keto group here, another keto group here. Okay. So I want to synthesize this molecule. This is my target molecule. How to synthesize this? I have to do the retro part. Retro part is very simple. I must do CC. Which CC I have to disconnect it? This is the best CC disconnection, where I need to have a carbonyl which is going to have a positive charge, another carbonyl which is going to have a negative charge. Okay, fine. So now you try to see this the corresponding this starting material. Okay, you have a suitable starting material for this. which is nothing but your simple acid halide, okay, from which you can get this particular acyl cation, okay. But what is this particular one? How to get this? So there is no suitable synthon, okay, because you have a carbonyl, oxygen is going to have a negative charge and carbon supposed to have a positive charge. So here also it's a inverted polarity. Now how to get this? I want to have a carbon which is having negative. So what you need to do, you try to take a substrate, okay, see for example this kind of substrates, where instead of having a carbonyl, I have introduced some heteroatom to this. So once I introduce some heteroatom to this, if I am going to add a base to this, I will be getting a negative charge. Okay, so this is nothing but your acyl anion. Okay, anion. Okay, this acyl anion I just given to one of the students. So acyl anion synthons. Okay, so how to get a acyl anion synthon? So you try to convert the CW1O into some derivative of that. For example, you have 2 sulfur atoms here, and with the 6 member ring. You can also have a 5 member ring also. Okay, SCH3. Okay, it's very simple. Yeah, thiol reacts with your carbonyl group to give rise to disulfide. Okay, so now you are able to generate a negative charge. So now once you make this kind of what you call a protected one with the sulfur atoms, so with the heteroatoms, I can also have oxygen also here. Okay, this also I can have a 6 member ring, 5 member. It's nothing but if it is going to be oxygen base, is called acetols. Okay, I'm sure I might have discussed with you in other aspects where a keto group reacts with the diol to give rise to acetol. Okay, so I have synthesized a negative charge species here. Now I can do comfortably, I can carry out my synthesis. So take a negative charge species here. Okay, sulfur. Okay, I've generated a negative charge species. Okay, I generated a negative charge species. This negative charge species can attack and excess gets eliminated. So I will be getting a what you can call a compound of this kind, where I have 2 sulfur atoms, okay, and methyl groups here. Okay, now what is my target molecule? So my target molecule is having a keto group. Okay, so what I need to do, whatever I protected, see this is nothing but a protecting keto group. So I protected using a dithiol. Okay, now I need to do the deprotection. What is the deprotection? Means I must remove these 2 sulfur atoms. These 2 sulfur atoms can be easily removed by simple acid catalyzed reaction. So once I remove that, I will be getting back my keto group here. Okay, so by making use of what you can call this kind of opposite polarity. Okay, what is the opposite polarity? A carbon supposed to have a positive charge, but I am having a negative charge. Okay, so this kind of opposite polarity, or it's also called inverted polarity. They are called Umpolung reagent. So here is a case where I can able to generate acyl anion synthon by using a what you can call a simple, either thiol or disulfide system. Okay, to get this particular. So whenever you go for this kind of what you call a protecting group, okay, whenever you go for this kind of protecting group, you must also keep in your mind how to deprotect it. The deprotection should be very easy. Then only finish. So then only we can have what you can call simple, the retrosynthetic analysis. So very simple retrosynthesis where I can able to convert this keto group into some other form where which I can accommodate a negative charge at this particular carbon Okay, and that can be used as a synthon to give rise to the product here. Okay, fine. So maybe I'll give you some more examples later. Okay, thank you.